More physics. Chapter 10. We're going to do the second assignment on your pacing guide, which is these problems here. Number 27. It's going back to what we did in the last assignment. The record turntable is rotating at 33 1/3 revolutions per minute. A watermelon seed is on the turntable. Sorry about that interruption there. We're going at 33 1/3. Sorry about that. I can make up my mind whether this was a decimal or mixed number. Like that. A watermelon seed is on the turntable. 6 centimeters, 0.06 meters from the axis of rotation. Calculate the acceleration of the seed, assuming that it does not slip. What is the minimum value of the coefficient of static friction between the seed and the turntable if it doesn't slip? And suppose that the turntable achieves its angular speed by starting from rest and undergoing a constant angular acceleration for 0.25 seconds. Calculate the minimum coefficient of static friction required for the seed not to slip during the acceleration period. All right. Getting a little ahead of ourselves, I guess. Let's do part A first. Calculate the acceleration of the seed, assuming that it does not slip. So, centripetal acceleration is equal to v squared over r, or omega squared r. Right? So the centripetal acceleration is equal to, I need to convert this first to get from revolutions per minute. So maybe you can just, I'm going to change that into a little multiplication sign, do my dimensional analysis. So 1 minute is 60 seconds, so I need to divide by 60, and 1 revolution is 2 pi radians. So 33 1/3 divided by 60 times 2 pi, about 3.5. Okay, so that means my centripetal acceleration is equal to omega squared r. Oops, sorry, 0.06. So that would move that over one more place. So at 0.74, that would be my centripetal acceleration in meters per second squared. I think that's what they wanted for that part, isn't it? Yes. And that's its only acceleration. Since it's moving in this part, it's moving at a constant angular acceleration. It's in uniform circular motion, right? So the only acceleration is toward the center. Now, in part B, the minimum value of the coefficient of friction. Well, you remember problems like this. We have done this before. The coefficient of friction is the frictional force, rather, is the only thing keeping it moving in the circle. So that means the frictional force would have to be equal to the centripetal force. So frictional force is equal to mu mg. It's not on a ramp or anything, so the normal force is just mg. And the centripetal force would be mv squared over r, or m omega squared r. Right? Of course, we know what this is, right? So the centripetal acceleration, this, right, that we found here, would have to be equal to g. Would have to be, I crossed out the wrong thing. It would have to be equal to mu times g, or mu, in other words, would be the centripetal acceleration over g. And our centripetal acceleration is 0.735, 0.74 divided by 9.8. So the minimum coefficient of static friction would have to be 0.076 about. Right? And then in part C, now it's going to accelerate starting from rest and then undergoing a constant angular acceleration for 0.25 seconds. So I'm going to use the equation that right here. So I know that my final angular speed is 3.5 radians per second, right? That's up to speed. And I want to know, what if we try to do that in 1/4 of a second? And then if this is just 0, my initial starting from rest, right? So that dividing that by 4 is the same as multiplying, dividing by 1/4 is the same as multiplying by 4. So my angular acceleration, excuse me, is about 14 radians per second. And for this watermelon seed, which is, where is it? It's at a radius of 0.06. So the tangential acceleration, because it's getting faster and faster as it goes around the circle, its tangential acceleration would be this times 0.06. 0.84 meters per second squared. So I know the accelerations, this is its centripetal acceleration, this is its tangential acceleration. So if you picture here, if you picture yourself on a boat on a river with, just kidding. So if it's going around this way, like this, then the centripetal acceleration is toward the center, and the tangential acceleration is tangent to the path. That's why it's called tangential acceleration. So the total acceleration is the sum of these two vectors. So it's actually, if you add those together, you move this one to here, this is the total acceleration here. So we need to Pythagorize these. So the acceleration total is equal to the square root of 0.74 squared plus 0.84 squared, which is about 1.12 meters per second squared. And now I just need to redo the calculation here to find that coefficient of friction. So it's going to be the same thing. My coefficient of friction will be 1.12 divided by 9.8. So now it has to be that 0.11. So it has to be have to have a greater coefficient of friction. That makes sense, right? If it's accelerating up to speed, you're going to have more friction to keep it, to make that acceleration possible. All right, that's a good problem. Like that one. And now, the kinetic energy of rotation and moments of inertia. So we'll review some of those formulas as we go through here. Number 33, very straightforward. The kinetic energy of rotation is one half I omega squared, where I is the rotational inertia or moment of inertia. So if I've got something with kinetic energy of 24,400 joules equal to 1/2 I times, it's rotating at 602 revolutions per minute. So just have to convert that real quick. 602 revs per minute is equal to, 1 rev is 2 pi radians, and 1 minute is 60 seconds. So we've done this a few times before, right? 602 times 2 pi divided by 60, about 0.65 radians per second. And you got to square that. So 24,400 times 2 divided by 0.65 squared. So it looks like about 116,000. And then remember what the units are for this. It's a mass times a radius squared, so kilogram meters squared. So about 116,000 kilogram meters squared. That's our rotational inertia. All right. I think I did that right. You can check the answer. If there's anything wrong there, it's just for silly math. Number 35, 2 uniform solid cylinders. Remember what the rotational inertia of a cylinder is. It's equal to 1/2 mr squared. Right? Rotating about its center, longitudinal axis, at 235 radians per second. They have the same mass of 1.25 kilograms, but different in radius. So what is the rotational kinetic energy of the smaller cylinder of radius 0.25 and the larger cylinder of radius 0.75? All right, so the smaller one, we have 1/2 I and the I here is 1/2 mr squared times the radius squared. So that's 1/2. That's the moment of inertia of a cylinder times omega, which is 235 radians per second squared. Let's see, so that's 1/2 times 1/2 times 1.25 times 1/4 squared times 235 squared. So that's about, let's say, 1,080 joules with 3 sig figs. And then the kinetic energy of the other one is exactly the same calculation, but with a different radius. Everything else is the same. So I'm going to go ahead and just bring back that and change that to 0.75, and that gives me about 9,700 joules. And so notice, I think the point they're trying to make in this problem for us to observe is that if you triple the radius, because the radius gets squared in the moment of inertia formula, that's not going to triple this, it's going to increase it by a factor of 9, right? Because it's getting squared here. 37. Calculate the rotational inertia of a meter stick with a mass of 0.56 kilograms around an axis perpendicular to the stick and located at the 20 centimeter mark. So here's the center. I know that the moment of inertia about the center of mass for a thin rod is 1/12 mr squared, right? Or r, sometimes we use L here, the length of the rod, right? 1/12 ml squared. And we're going to move that, so I'm going to have to do the parallel axis theorem. So my new shifted version, it's the original one plus m times the shift squared. So let's do that. So the original around the center of mass would be 1/12 the mass of the stick, which is 0.56 kilograms. That's a heavy meter stick. Times the length squared plus m times the shift. So this is if this is the 0 end, here's the 20 centimeter mark. That's actually shifting 30 centimeters, right? So from here, the 50 centimeter mark to the 20, that's a shift of 30 centimeters, or 0.30 meters. So that should give me my new my new moment of inertia. So I've got 1/12 times 0.56 times 1 squared plus 0.56 times 0.3 squared. So that's about 0.097 kilogram meters squared. Number 39. Trucks can be run on energy stored in a rotating flywheel. With an electric motor getting the flywheel up to its top speed of 200 pi radians per second. One such flywheel is a solid uniform cylinder with a mass of 500 kilograms and a radius of 1 meter. So that means its moment of inertia would be equal to, for a cylinder, it's 1/2 mr squared. So that'd be 250 kilogram meters squared. What is the kinetic energy of the flywheel after charging up? So that means at its maximum there. So the kinetic energy of the flywheel would be 1/2 I omega squared, which is 1/2 times the moment of inertia, which is 250, times omega, which is 200 pi. So let's see, that's half of 250, that's 125 times 200 pi squared. That's a lot. 1, 2, 3, 4, 5, 6, 7. So about 4.9 times 10 to the 7th joules. Part B. If the truck uses an average power of 8 kilowatts, for how many minutes can it operate between chargings? That's an interesting question to bring us back to what watts are. So 8 kilowatts would be 8,000 watts. And if you remember what a watt is, that's the rate at which energy is consumed, measured in joules per second. So if it's going to if it's got this much energy and it's going to use 8,000 joules per second, I can just divide here. So I have this much energy to start with, and I'm going to use 8,000 per second. So that's going to last me for about 6,200 seconds or so, right? And if you wanted, you could turn that into hours. You could divide by 3,600, so about 1.7 hours, if you like. And, oh, there is no part C, just kidding. Number 41, last one. So let's see. In this figure, we have two particles, each with a mass of 0.85 kilograms. They're fastened to each other by two thin rods, each with a mass of, I'm going to copy this thing down. So, and that's the axis of rotation here. And we want to find the rotational kinetic energy, the rotational inertia. First in part A, we want to find the moment of inertia, or the rotational inertia, and then we want to find the kinetic energy. So let's see, what do we have here? I've got these things are 5.6 centimeters and have a mass of 1.2 kilograms, and then the particles have mass of 0.85 kilograms. So just like masses, we just have to add up all the moments of inertia. I'm going to treat this like one long rod. And a rod about its end, that's one that we're going to see a bunch of times. You can do it with the parallel axis theorem, but it's 1/3 ml squared. So that's a good one to know. It's about the center, it would be 1/12 ml squared, but a rod about its end is 1/3 ml squared. You can easily prove that with the parallel axis theorem. Okay, so that means that for the rod, for the whole thing, I'm just going to treat it like one long rod. We have 1/3. The total mass would be 2.4 kilograms, times the total length of it would be 0.112 meters, right? 0.056 times 2. So that is going to be 1/3 times 2.4 times 0.112 squared. So that's about 0.0100 kilogram meters squared. And then each of these particles, particle 1, it's just a particle, so particles just have moment of inertia mr squared. I'm going to treat it like a particle anyway, so that's m times r squared, and then particle 2, m times r squared. So let's do those. 0.85 times 0.056 squared. That's 0.0027 kilogram meters squared, and same thing but 112. That's 0.0106. And then to find the total of the whole contraptione, we just add all those up. So 0.01 plus 0.0027 plus 0.0106 is 0.0233 kilogram meters squared. Sometimes the book will do these in different units, but I always like to just go to SI units. So you can reconcile that with the back if theirs is in different units. And then that was part A. Part B, we just want to know what's the kinetic energy, which is 1/2 I omega squared. 1/2, there's my I, 0.0233. If it's rotating at 0.3 radians per second. So I've got this number times 1/2 times 0.3 squared, which is 0.001. Right? And that is the end of that assignment. I hope I got all the answers right.